Okay, now that we've covered one of the example parts of the parallel search stream gang, we're going to continue on. And if you recall, what we had talked about at the end of last time was some of the pros and cons of the parallel search stream gang implementation. And the pro basically was that it was really easy to make it parallel just by changing stream to parallel stream. That was good. And it was very declarative, all the things it inherits from being part of the search stream gang design. But there were some limitations. And one of the main limitations was that it didn't fully maximize the use of parallel computing. So that's what we're going to do now. We're going to talk about how we can use a so-called ParallelSpliterator to improve the performance of the stream. And so it's basically going to address a con from the previous approach where we didn't get as much parallelism out as we wanted. And then we'll also then talk about the pros and cons with this solution. And that'll then motivate some other stuff we'll talk about later. So what's the ParallelSpliterator? Well, we have a new search implementation called Search with ParallelSpliterator. And that's yet another implementation strategy that we use. And you can go and see the implementation here. I'll show you the key parts in a second. So as you can see, we have about 8 to 10 different implementations. This is the one that we're about to talk about. So this uses parallel streams in 3 ways. The previous approach we saw used it in 2 ways. This is going to use it in 3 ways. So like the previous solution, it's going to search chunks of input in parallel. So it's going to take the input strings. Remember, each input string is a work of Shakespeare, right? So it's going to search those in parallel. And then it's also going to be searching for phrases in parallel. So remember, we have phrases like, neither a borrower nor a lender be, or to thine own self be true, or all this other highfalutin Shakespeare quotes. So those things will be searched in parallel. And that's what we had done before. But now we're going to go one step further, and we're going to search for chunks of each input string in parallel. So if we have a big string with, like all the words, all the scenes and acts and so on in Hamlet, we're going to break up that string into chunks and search those strings and the chunks of the strings in parallel as well. And that's different, that's new. So this approach is the most aggressive parallelism strategy we've looked at so far. So it's going to basically be parallel in pretty much every way you can imagine, right? Parallel in the input strings, parallel in the input phrases, and parallel in the chunks of each input string. So we're going to really maximize parallelism. And you'll see even in my modest quad-core laptop, which is by no means the cutting edge of multi-core these days, we're going to see a big performance boost by doing this. So just to show you this, I'd written a little program. This is very similar to the SearchStreamGang. It's called SearchStreamSpliterator, except what it does is it tries every possible combination of parallel and sequential. So remember that you can have parallel in the input strings, parallel in the input phrases, parallel in the chunks of input strings. So you got 3 different choices which could be sequential and parallel. So that's 2 to the 3. So we basically end up with all these different ways of doing this. So we have 8 different combinations. And what you see is if everything is sequential, then it takes this amount of time to do the searching. And if everything is parallel, it takes this amount of time. So you can see it's a pretty nice speed up. It's super linear, as we might say. And this is when we looked up each string being a different work of Shakespeare. Okay? Here's what we do when we took all the works of Shakespeare and we split them into 2 chunks. Twelfth Night to Macbeth as one chunk, and then Hamlet to As You Like It as the rest. Who knows? So they're basically split in half. So now each string is way bigger. And what you notice here is that it's a little bit faster, not a whole lot faster. And the reason why it's a little bit faster is because we have bigger strings, and therefore doing parallel searching of the strings will go a little bit faster as well. So the more data you have to work on, the better the win you get by parallelizing it. That's kind of obvious, but it's good to see it actually pays off in practice. Okay, so this is what the program looks like. It's pretty interesting. The program looks almost identical to what we had before, with one tiny little change right here. This is in the process input method. So this is the one that's going to search the phrases in parallel. And what we're doing here is when we call search for phrase, we're going to pass in the phrase, we want to search for, like, neither a borrower nor a lender be, the input string, which could be the work of Shakespeare, and then instead of what we put before where we had false, which said do it sequentially, we put true. And this says break this input string up into chunks and search for the phrase in that input string in parallel. So that's what that says. Here's the actual implementation of search for phrase. What happens is we're passing in a Boolean called parallel, and we're going to call a phrase match splitterator, which I'll show you in a second. So phrase match splitterator is going to be used to break the input string, like Hamlet, into the chunks of phrases to search. And this is an extension of the phrase match splitterator we had talked about a little bit earlier, like a week or so ago, that used sequential searching. Now, a couple things to note here. The way this is going to work is we're going to call a method called streamSupport.stream. This is something you get from Java 8. And streamSupport.stream takes a splitterator, and it will split the input up into chunks. And depending on the value of the Boolean you pass in here, it'll either do it sequentially or it'll do it in parallel. So the good news is, at a high level, from an architectural point of view, there's really little or no change to this part of the program. We just go false to true, right? Really simple, minuscule little change. We'll see, of course, that complexity lurks somewhere, and the complexity, of course, is going to lurk in phrase match splitterator. That's where we push all the complexity. So let's go ahead and talk about this. So I think I mentioned before that the phrase match splitterator is a splitterator that works for either sequential or parallel streams. So it's like the Shimmer non-dairy floor wax. It's a dessert topping and a floor wax, so it gets used for both things. When we had talked earlier, we talked about the sequential version, where we just had a single thread that was doing this, the breaking of the input up into chunks using the try advance method. And now we're going to talk about the parallel version, where we're going to have multiple threads working on the input once it's split into parts. So once we've chopped up the input into pieces, like Mickey Mouse in The Sorcerer's Apprentice, then each of those pieces is going to be able to run in parallel. And of course, the whole purpose of this is to make things work better. And the reason it's going to work better is because we're going to have more things to work on with our multiple cores. We're going to keep the cores full and ready to go. Here's kind of where this happens architecturally in the program. So we will, by the time we get to this point, we will have taken our list of strings, which is the phrases. We will have turned them into a stream of strings. And then we're going to call an aggregate operation map with the behavior search for phrase. And that's where all the magic is going to happen. And what we'll end up back here with is the stream of search results. And this, of course, will run in parallel. So here's what we have to do. Now, this is what makes this particular splitterator a heck of a lot more interesting and complicated than the kind of splitterator that you guys have done to this point with things like array, the array class splitterator, where all you had to do was just divide it in half each time, right? Really simple. So what we have to do here is we have to be a lot more clever. So what we're going to do is we're going to take the whole input string, and I'm just taking a little piece of it here, but just imagine this is the whole string. And we're going to have to split this up into multiple chunks so we can search them in parallel. So the big question is, where do we do the split? Well, when you have just an array of longs, so an array of integers, the split is trivial, right? You just take the halfway point, and everything that's to the left of it is one chunk, and everything to the right of it is another chunk, and you just keep doing that process recursively till you have a tree of chunks, and then you throw those chunks into the fork join pool, and away you go, right? So deciding where to do the split is ridiculously fast, and it divides evenly, and it's great. When we do this for strings, it's a little bit more tricky. So here's one example. This case is sort of, when you get lucky and you split your input in half, and it just so happens that, let's say we're looking for the classic cliche, brevity is the soul of wit, and that appears in this big chunk of Shakespeare text. And we split this in half, and let's say we just happen to get lucky, and we do the split right at the end of brevity is the soul of wit. Things divide evenly, things divide efficiently, We don't split across phrases. Speed up is great, right? This is wonderful. That's the best case. But what happens if something goes wrong? What happens if we sort of naively split the input up and we happen to split it so it's equal, but the equality happens to cross a phrase we're searching for? Well, now we've got a big problem, right? Because when we search for the phrase here in this substring, we'll never find it because it got truncated. And of course, if we search for it over here, we won't find it because most of it's in the earlier phrase. So now we've got a problem, right? We won't be able to find what we're looking for. So the trick here is to write a spliterator that is careful to split as equally as possible, because we still want to have things pretty much balanced, and as quickly as possible, because we don't want to do linear search to find this stuff, but we don't want to split the input across phrases. So that's where things get tricky. Let's take a look at how we could do that. So we're going to implement a spliterator called phrase match spliterator. We've looked at some of this before. We looked earlier at the constructor, which is the thing that took the phrase and made a regular expression out of it that could span lines. And we looked at the try advanced method, which is the one that will go and see if there's a match within a substring for the phrase that we're looking for using regular expressions. So we've looked at that before. Now let's take a look at the hard part, which is the try split part. So try split is the part that's going to break up the input into chunks that doesn't span across the phrase boundaries. So there's the key method here is called try split. That's actually the one that's defined in Spliterator that we have to override and implement. These other ones are sort of implementation helper methods we do to make this implementation a little bit easier to understand. One of the things that you should note and remember, when a spliterator runs, it actually doesn't run in parallel. So splitting of a string is done, or splitting of a substring is done within one thread of control. Once the substring is split, then those resulting chunks, after they get down to a certain minimum size, are then enqueued in the queues for the fork join pool, and those things then run in parallel. So one of the consequences when we look at this code, there won't be any locks. There's no need to synchronize any of this, which is good because it means one less thing to have to worry about, one less source of accidental complexities that will get you into trouble. So here's kind of how the overall algorithm works at a high level. So try split, this is really what try split always does. If the input is below a minimum size, return null. When null comes back from try split, that's an indication to the streams framework, the parallel streams framework, that this input is reached its atomic size. Don't split it any further. And then take it and stick it onto a queue and run it in the fork join pool. So if you've reached a minimum size, you're done. In the context of searching strings, that minimum size actually is fairly large because there's no point in splitting strings up into character. You don't want to end up with a string that's been split up into character level chunks, because first of all, you never find phrases in it. And number two, it takes a long time to do all the splitting, and the win you get from searching tiny segments of strings isn't worth the effort to try to split them up to that level of fine-grained granularity. So you could actually have a fairly large minimum size when you're searching for strings. So assuming that we haven't reached that minimum size, we split the input up into two relatively even-sized chunks. And I'll come back and talk about what relatively means in this context. And then you return a spliterator for the left chunk, and the right chunk will update itself so that now you've got two relatively evenly sized chunks. And we want to do this evenly so that we don't end up with a lopsided tree, so things are about the same size. You don't have to have them be exactly the same size in order for splitteration to be a win. They just need to be close to the same size. Well, can anybody think about how you might do the splitting if you don't want to split across phrases? How might you do that? Yeah, Matt. Okay, so you could search the input. That would be one approach. You could search through there. The tricky part there, of course, is that you need to figure out where to start the search, right? If you start the search at the left-hand side, in other words, where the input starts, then you've basically turned what should be a very quick operation into a linear search of the string. So you could find a period, right? So you could do that. That'd be good. Anybody else have any other ideas of how you might do the split? Well, let me show you what I ended up doing. It turned out to be very subtle, but pretty cool. So here's the high-level view of try split. So what it does, and if you want to read the code, it's very heavily commented. I'm not going to give you all the comments here because they don't fit on the slide, but the actual code is very heavily commented. So try split is going to check to see if the length of the input is less than the split size, and if so, we're done. Otherwise, kind of as Matt said, we just start by saying, we'll split the thing in half. We'll see if that's a good starting point. Why not, right? So we start out by splitting it in half. And then we're going to call compute start pause and try to update split pause. And these are things that are going to figure out where we really need to make the split. And then when we're all done, we take the updated split position and we use that to actually split the array into 2 chunks, which may not quite be evenly sized, but they'll be pretty close. And the whole goal here is to avoid splitting things across strings. So let's take a look at this. This is the real workhorse method. This is try to update split pause. And we start out with the starting position, and we then go ahead and give the split position. And so what happens here is we take a look at the length of the phrase we're searching for, right? So we've got the big string, we've divided it arbitrarily in half, and now we take a look at the pattern we're searching for. And we're going to start by seeing whether or not that pattern appears in a way that will straddle the split, right? So first thing we do is we make sure that the phrase isn't larger than the split. If the phrase is larger than the input string at this point, we're not going to find it, right? It couldn't possibly be in there, so that's just a sanity check. But once we've done that, we then go ahead and see if the phrase spans the initial split pause. And the way we do this is we make ourselves a subsequence from the start pause to the end pause, and we make ourselves a regular expression that will search within that region, and then we go ahead and we try to see whether or not the substring is found anywhere within that region. And if it's not found within the region, then we know it doesn't straddle the split. If we do find it within the region, then we have to go ahead and update things to take into account where the match occurs. And so we'll then basically end up making the split pause be at the place where it's going to straddle. So we make sure we don't split across the phrase. So that's what all this is doing. And it's very clever, and it uses regular expression matches in order to make this work. And it's still reasonably efficient. It's not going to take linear time. It'll take basically constant time to do this. So if there is a match, if we find a match within that region, then we go ahead and update the split pause to handle the phrases that span new lines and span the split. Once we've figured out the actual split, then we're going to go ahead and split the input up into 2 chunks based on the split pause, and then we go ahead and update our right-hand side's input sequence, because now it's about half as big as it used to be, and then we create ourselves a new phrase match spliterator, which has the left-hand side part. So the left-hand side part's what's returned from split input, and the right-hand part updates itself by modifying this object. So it turns out that that's actually not an easy thing to do. In fact, I'll say this later when I do the review of this, when I looked at all the time I spent writing the program, the bulk of the time was spent getting the spliterator to work properly. But we'll see in a second that that was a smart thing to do. So once we got the input into chunks, then those things will also be processed within the common fork join pool. So we'll have chunks, we'll have input strings, we'll have phrases, everything will be running in parallel. So the good news is that without a lot of changes to most of the program, pushing all the complexity into the spliterator, we're able to get a nice boost in performance. So this is the original performance with the very simple splits we did earlier, we talked about last time. Here's the new benefit by splitting even more aggressively in an even more fine-grained manner with the parallel spliterator approach. And you can see that on my quad-core laptop. That's performing quite well. Again, super linear speed up. Interestingly enough, I think I mentioned this before too, when I ran this on my MacBook, which is actually what I'm presenting from, that has faster processors, so it's almost 3 gigahertz, whereas this is 2.7 gigahertz. And so the actual absolute running time is faster. And also, interestingly enough, for a variety of reasons, parallel streams ran pretty darn fast as well with this approach too. So the point of this is, by getting finer grain parallelism, we're able to improve performance because we keep the cores busier, which is not, again, a too surprising result, but it's good to see it actually work out in practice. And so if you play your cards right with relatively little effort, you can get real good performance. Now, if I had an 8-core laptop or a 16-core laptop, you should expect to see, again, a speed up into the point where there really isn't any more work to do in parallel, right? So you would probably see pretty much a linear speed up. Why would we expect to see pretty much a linear speed up for this kind of a program? What's the reason why that would work so well? What's the characteristic of this kind of program that lends itself nice to parallelization? It's embarrassingly parallel, right? We're ashamed at how parallel this program is. And why is it embarrassingly parallel? Right. So we're splitting up the input strings, right? The works of Shakespeare. We're splitting up the input phrases, the phrases we're looking for. We're splitting up each input string, and there's no need for locking. There's no need for any of the other things that come along with concurrency in order to make it work. It just kind of magically gets faster and faster. And that's great when your problems work like that. It also shows the little work was required. We just changed, true to false or false to true, and boom, it ran better. Of course, as we'll see in a second, making the Spliterator was not easy, right? That was like rolling a rock up a hill. It was very tedious. So the main con with this approach was that the Spliterator is where all the effort went into. And you've got to make sure you do the split carefully. When I first wrote this program, I was very pleased at how it performed, but I had some bugs in my code. So I didn't really discover those until we used some unit tests to reveal the fact that things weren't always working properly. And that was a very useful lesson, which I sort of knew, but I just was too busy with other things to write the unit test first. As a general rule of thumb, the more complicated the code, the more important it is to have the unit test to catch the problems. And you'll undoubtedly find that as your assignments get more complicated, the unit tests make a big difference. Okay, so writing the Spliterator took more time than anything else, and that's because it's the part of the code that required careful, X-Acto knife level precision in order to get the behavior correct. Okay, any questions about that?